All right, today we're going to tackle a concept that's absolutely fundamental to physics, engineering, and even video games, the parallelogram law of vector addition. I know, it sounds super complicated, right? But don't worry, we're about to break it down in a way that's incredibly simple and really visual. So let's just dive in.
But you know what? Instead of starting with some dry, boring definition, let's kick things off with a little puzzle. It's a scenario I think you can easily picture.
So really think about that for a second. You're pointing your boat directly at the opposite bank. You're rowing as hard as you can, aiming for a perfectly straight line. But the river has other ideas, doesn't it? It's pushing you sideways. You're definitely not going to land directly across. So what actually determines where you end up?
And here's the key to the whole thing. Your boat is experiencing two completely separate motions at the exact same time. You've got your own effort pushing it forward, and then you've got the river's current pushing it sideways. To figure out our little puzzle, we need a way to combine these two things into one single true path.
And for that, we need the right tool for the job. And this is where we bring in a concept you've probably heard of, but maybe don't think about every day: the vector.
So what on earth is a vector? It's actually really simple. It's just a measurement that tells you two things: how much of something there is and which way it's going. That's it. We usually draw them as arrows, where, the length of the arrow shows the how much, the magnitude, and the direction it's pointing is, well, the direction.
To really get a handle on what a vector is, it helps to look at what it's not, and that's a scalar. A scalar is just a plain old number. So if you say your speed is 5 kilometers per hour, that's a scalar. But if you say your velocity is 5 kilometers per hour north, see? Now you've given us the full story. You've got the magnitude and the direction. Now you've got a vector.
This whole idea becomes absolutely crucial when you have more than one force at play. Just like with our boat, right? We have the force from your rowing and we have the force from the river current. To find out what really happens, we can't just add the numbers together. We have to add the vectors. So, how do we actually add these vectors? Well, this brings us to the star of today's show, a beautifully simple and visual method called the parallelogram law. Okay, that's the official textbook definition. And I'll admit, it sounds a little dense. But all it's really describing is a super simple way to just draw a box that magically gives us the answer. Seriously, let me just show you.
It really is just 4 simple steps. First, you take your 2 vector arrows and you put them together so their tails are touching. Step 2, you basically build the box. You just sketch in 2 more lines, each one parallel to the opposite vector. Third, you draw one single line, the diagonal, right from where you started to the far corner. And that's it. That diagonal line is your brand new vector. We call it the resultant, and it represents the combined effect of the first 2.
All right, so we've got our puzzle, and now we've got our tool. Let's head back to that river and finally figure out where in the world our boat is actually going. Okay, here we go. We can imagine you're rowing as one vector, an arrow pointing straight across the river. And the river's current? That's another vector, an arrow pointing downstream. And just like we learned, our first step is to place them so they're tail to tail. Now for step 2. We just sketch a line that's parallel to the river's vector, starting from the tip of the boat's vector. Then we do the exact same thing for the other one. Draw a line parallel to the boat's vector from the tip of the river's vector. And look at that. You can see it right there. We've built our box, our parallelogram.
And now for the grand finale. We draw the diagonal, right from that starting point to the opposite corner. And this right here, brilliantly shows us the boat's true path. The length of this new arrow tells us the boat's actual speed, and its direction shows us exactly where it's headed, diagonally downstream. That's our resultant vector. Pretty cool, right? And what's so amazing is that this isn't just some neat trick for solving boat puzzles. This exact same principle is being used everywhere. It's what calculates a plane's real flight path when it's being blasted by a crosswind. It determines which way a heavy box will actually slide when 2 people are pushing it from different angles. It is literally running inside video game engines right now to make the physics and movements look realistic. It's the same math, from planets to pixels.
So really, this law is a tool. It's a way of seeing the invisible forces that are constantly shaping motion all around us. It lets you take a bunch of different inputs and get a single predictable outcome. So the next time you see leaves scattering in the wind or you watch a ball curve through the air, just think about this. What hidden vectors are at play? What forces are combining right in that moment to create the path that you see?